recording. 18E is called absolute minimums. This is different to the maximum that you're familiar with. So when I draw the picture again, when you get a curve, something like this, actually I'll do it again, something like that. Okay, in this curve, we can say a couple of things. There is a maximum which you call local max. There is a minimum which we call local minimum. And there is also, even though the way I drew it looks a bit funny, there is an inflection point and then an end point. So there's two endpoints there. Endpoint. What you learnt last session when I talked about 18C and 18D was called stationary points. Remember, stationary points is when the gradient of the tangent line is equal to what again? Stationary points occur when gradient is 0. Okay, and gradient 0 means that. It's a horizontal line. So your tangent line, when you draw a tangent at any point on that curve, if it's a nice horizontal line, you either have three scenarios. You have a local max, so you can only get a tangent line that is horizontal at a max, or at a minimum, or at an inflection point. See what I mean? So these are the three. So that's 18C, 18D. 18D is to determine the type. 18C is to find those points. Yeah? But when you say the word maximum, the reason why we call it local maximum is because the graphs can have a local maximum, local minimum, local max, local min, but then this is the absolute maximum value because it's the highest value that you can get. So there's a difference between absolute max, meaning the highest value you can have, and absolute minimum is the lowest value that you can have versus an actual turning point. So each one that turns, does a little curve, that's a turning point. That's called a stationary point. So you can have a maximum. So that's why it's weird to say that's a maximum. So they call it a local maximum because it's localized. Okay. So the language here in your notes, when they say absolute maximum, it refers to the largest or highest value the function has, but this is actually the largest y value. So fill that in. It's the largest y value. So when you're looking at the function, you're looking for what is the highest y value it can have as an absolute max. An absolute minimum means what is the lowest y value the graph can take. So in the scenario that I drew here before, the local max happens to also be an absolute max. That's true. The absolute max is the local max because that is the highest value it can have. However, I should have done it differently. But this local minimum also happens to be the absolute minimum. I should have drawn a different graph where some students, like this one, that's a local minimum and absolute minimum, but that is not that's not a local maximum. So this one here is an absolute max. This is a local max. This is a local max. And this is min. Local min, local min. So these points, just because you find a stationary point, it doesn't mean that it is always the highest or lowest point. So this is why in this exercise, you also have to test endpoints. You have to check what is the highest y value you can get for not only stationary points, but also the endpoints. That way you can kind of figure out which one is the largest and which one's the smallest. Okay? And the problem with it is that there are some graphs that you won't be able to picture. And that's why learning to find stationary points gives you some information. Okay, so let's do some examples just to get you feeling how to do it. That's the idea. So that's the difference between absolute max versus local max. Okay, local max is localized, turning points. Absolute max and absolute min just means the highest y value, lowest y value. Let's go to this problem here. Let's have a look at this problem. Example 12 of your textbook. They've given you a graph, x squared plus 2. Find the absolute maximum. That means find the largest y value this graph can have based on this equation. X squared plus 2, what type of graph is this? X squared plus 2 is a, what is it, Numafi? What type of graph is x squared plus 2? Parabola, which is quadratic, okay? We can see that the plus 2 tells us what? What does plus 2 tell us? Let's go with Mete. Good, so it goes up by 2. So I can tell this is a smiley shape, it's positive, and it goes up by 2. So it might look something like this. Okay? But the graph doesn't go infinitely left and infinitely right because they've given us a restricted domain. Okay, so this tells us that x is only between -2 to 4, and the square brackets means equals to or inclusive. So it only goes from -2 to +4. So that means I have to cut it off. I have to say, well, 2 is probably around here, and 4 will be double that length. So let's say 4 is over there. That means I need to cut off the graph at this point and this point. Means I don't sketch this bit and I don't sketch anything beyond 4. So if I sketch it again, it should be something like that. That's what I'm picturing at the moment. Okay? Now let's think about it. Based on this equation, when x is 4, what is the endpoint y value? So that point there, if x is 4 and the function is x squared plus 2, what should the y value be? 18, very good, because 4 squared, which is 16, 16 plus 2, 18. Same thing with the 2. 2 squared is 4, 4 plus 2 is 6. So this point is 2, 6. Now that I've got a graph, I found the endpoints. Usually, it wouldn't be as easy to know what the turning point is, but because it's a parabola, I already know it's 0, 2. But if you didn't know, how do you find the local minimum here? So clearly the graph is going to be a local minimum, but how do you find it? What do? How do you find this point, 0, 2?
Maybe make the derivative equal 0.
Beautiful. That's what you're meant to do. So that they'll give you a bunch of equations. Some of it is quartics, some of it is cubics, some of it could even be quintics, right? And you don't know what the graph looks like. This one's easy because it's x squared. But if it's not x squared, you need to be able to know what to do. So in this case, yes, Mete is right. We want to check if there's any stationary points. Clearly, a parabola should have a stationary point. So stationary points occur when the derivative is equal to 0. Let's go. What's the derivative of x squared plus 2? Let's go with Anthony. 2x. Beautiful. So we say stationary points. So stationary points occur when derivative is equal to 0. So we solve for it. We say, okay, derivative is equal to 2x, so I'm going to make it equal to 0. Turns out to be, divide both sides by 2, x is 0. So this means at x equals 0, the derivative will equal to 0. But that only means that you just found x cornered is 0. You still don't know what y is. So how do you find that stationary point? I know it's 0, 2, but you got to prove it to me. Show me how I would get 0, 2. So how am I going to get this y value? Adi. Very good. Not this one. Not the derivative. The derivative tells you the gradient. You sub it back into this one. That tells you the x and y. So subbing back in, f of 0 is equal to 0 squared plus 2. That gives you 2. And that's how you get stationary point of 0, 2. Usually you don't have a graph to be able to tell, so then you have to do a gradient table to figure out if it's a minimum, inflection point, or a maximum. That's what last session was about. Okay? So if you answer the question now, if you found the endpoints, so sub in to find endpoints, 2, 6, 4, 18. So we've got endpoints. We found stationary point, 0, 2. So hypothetically, this is what you would have done had I not drawn the picture for you. You would have had 2, 6, you would have done 4, 18. So you knew 18 was up here. And you would have had 0, 2 there. Then from here, now the question is asking, what is the absolute maximum value and the absolute minimum value? You then can connect because you know this is a local minimum. Do the turning point. Then you can actually then say. So from here, you then say, yep, clearly absolute minimum is at 2. So absolute minimum. So you got a 2 because that's the y value. We're interested in the y value, not the x value. So absolute minimum is 2. What is the absolute maximum in this case? 18. Very good. It's the y value. The largest y value you can have. It's 18. Some students will write 4. Okay. Well, sometimes they even write 6 or 2. Okay, so looking at the graph, and it's tricky when I give you an equation that you're not familiar with. So I started off with a quadratic. It's easier to do, but the only year 11 part or calculus part was this bit. Stationary points, so 18C, 18D, determining what type of stationary point you have, subbing endpoints, and then understanding what's the difference between absolute max and local max. It's all about analysis of the graph. Problem is, can you get the graph to begin with? Okay. All right, let's do another problem. Flip over the page. Flip over the page when you're ready. So these notes are here. Notes are here. The idea is trying to sketch. You're going to get a problem where you can't know the equation. This one is a quadratic. It was easy, but let's give you one that actually maybe most of you do not know what it looks like. Flip over the page. Let's try this one. So this one now it's an application, but still the same idea. You got a cubic equation. 4x cubed minus 8x squared plus 4x is not something that all of us can picture without a CAS, right? So we're going to try to do this without a CAS where you can tell me what is the absolute max, absolute min, and what are some stationary points. Doing the same skills I just taught you. Okay, so let's do it again. Let's have a think. This problem is a square piece of metal. So here we go. We've got a square piece of metal. And side length 2 meters. 4 squares are removed. So you can see 1, 2, 3, 4 squares have been removed. So this bit here has been taken off. This bit here has been taken off. This bit here has been taken off. And this bit here has been taken off. So 4 squares have been taken off. They tell you it's a side length of 2 meters. So from here to here is 2 meters. And because it's a square, both sides are 2 meters. So far, so good. They say the metal is then folded along the dash line. So I must have removed certain amount. So I'm going to write X here. I'm going to remove X amount, remove X amount. And I'm going to fold it up and I'm going to get this particular open box. It'll look something like this. Something like that. Okay, so if you fold it up, you get a box, 3D box. Open on the top. Okay? Now, once we've got the visual aspect, so where I fold it, this must be X. What's the length of this box? 2. Close. This is 2 meters. But remember, I remove this amount and remove this amount, and then I folded it up. So this is the base of the box. Question is, how far is the base of the box? Anyone know? It's the application component. Very good. So most students say 2 minus x, but it's not just x. There's 2 of them. You're removing 2x lengths there. So there's 2x lengths here. It's 2 minus 2x. There's my length here. And that also means this must be 2 minus 2x as well. So when you put it together, when they say, question A, show that the volume of the box is given by this, where'd that come from? Well, volume of a rectangular prism is length times width times height. So here we go. Volume is equal to length times width times height. Length is 2 minus 2x times 2 minus 2x times the height, which is x. Because this is a show that question, you cannot do this on your CAS. You have to do it by hand. You have to expand it. So we go, let's expand it. This becomes 2 minus 2x squared times x. Using your expanded formula from quadratics back in term 1. What's the expansion of 2 minus 2x all squared? Can I please have, let's go with Christina. What is 2 minus 2x all squared again? Beautiful. Okay, for those who've forgotten, it's ax squared plus b, a squared plus 2ab plus b squared. That was the formula for it. So square the first one, double these two times to each other, and then square the last one. That's how you get the bottom one. And then you expand it from here, so you can see x times 4, x times 8x, and 8 times this. This is how you get 4x cubed minus 8x squared plus 4x. And that is how you prove this is equal to that. So when they say show that, every step has to be shown and how you get there. Okay, so that expansion is key. All right, so now we've got the formula. We've got V in terms of X. Great. If it's a CAS calculator, you can put it into your CAS and define it, and then you can sketch it. But we're trying to do this without the sketching of a CAS, right? So first one says, find the X values that gives the box its maximum volume. Okay, so be careful there. So this graph here, when they say maximum volume, that means this cubic graph, let's hypothetically draw it like this. This cubic graph has to have a point somewhere where it reaches a maximum, or potentially it could be like that, or it could be like this. We don't know how the cubic looks, but we know it could be like this, or it might even be like this. We don't know what the absolute maximum value is yet. Okay, so when they say maximum volume, it could be an endpoint. It could be a turning point. We don't know what the graph is, because if it goes only from here to here, then this is clearly the maximum point. This is a local max. So what you have to do now is all the skills that we just learned, find the stationary points, find the end points, and then determine what is the highest y value you can have. So let's start off. Let's go endpoints first. What is the restriction when it comes to volume and x length? What can't you have? So for volume, what can't you have? So volume, what's the restriction on volume? Can't have negatives. Very good. Can't have negatives. Same thing with x. X is how much you're cutting off. Now, how much are you cutting off? Well, there's a limit. X, you can't take off 5 because there's only 2 meters. So really, x has to be bigger than 0, but it also has to be less than 2. But technically, it has to be even less at some point, okay? Because it can't be too big, right? So what you need to be careful of is when you're looking at conditions, make sure to check where the conditions truly are, where the domain restrictions are. But let's just start off. Endpoint, when x is equal to 0, volume is equal to 0. You can see that. So the endpoint starts off at 0, 0. So we've got an endpoint, 0, 0. Cool. What else do we also have? We could say, when will it actually touch the x-axis? Because we know volume can't be negative. You have to find when it touches the x-axis. How do you find when it touches the x-axis? Solve for when volume is equal to 0. This is what you want to solve. This is back to term 2. Obviously, this is an application question, so you can use a CAS, but if you couldn't, if it's exam 1, this one you actually have to factorize and solve. Which, conveniently, you can do it by hand because they all have a common factor of x. Let's take out x as a common factor. So here we go. We get 0 is equal to, so I'll write here endpoints. So you're looking for endpoints. Take out x as common factor. You get 4x squared minus 8x plus 4. In fact, you can probably take out 4 as a common factor as well. So let's take out 4x. You get x squared minus 2x plus 1. Factorize this, so that's 4x. What is the factorized form of x squared minus 2x plus 1? What's that factorized to? Good. X minus 1, x minus 1. So that means You get 4x bracket x minus 1 squared. So where are my x-intercepts then? Clearly it's at 0 and 1. Very good. Because you're solving for when it equals 0. X minus 1 needs to equal 0, so x has to be 1 for that to work. So conveniently, we've got two axis intercepts there. So it's 1, 0, and 0, 0. What's the graph look like? So hopefully you remember from last term when we did chapter 7. What happens when I put a square on a linear factor? What does happen to the graph again? Anyone remember? Because we have to sketch this graph. We know it's cubic, so it has to either look like this or it looks like this. Right? It's a cubic graph. Cubic graph has a maximum of 3 intercepts, but right now I've got 2. So the only way to get 2 is if the graph crosses through one, touches the other, or touches one and then crosses through the other. At 1, 0, there's a square. What does that mean? It touches. Yeah, so remember how I said if it was cubed, then there's an inflection point there. If it's squared, it touches the curve. So this is where at exam 1 level, you're meant to be able to picture it and say it crosses through 0, but then it comes back and touches 1. And the reason why I know it touches 1 is because there's a square there. Okay, so technically the graph is meant to continue. But we're going to stop here because its volume can't be negative, x can't be negative. So it must be something like this. Problem is that you can't have infinite x length. Doesn't make sense. So likely your volume has to then stop somewhere here. That clearly indicates to me that the maximum volume that you can have must be a stationary point. That's then when you use stationary points to do. See what I'm doing? So you have to work out endpoints, figure out roughly what the graph looks like, and then you sketch it. So what are some restrictions for x in this application context? Well, we knew volume had to be greater than 0. X had to be greater than 0, but there was a restriction to it. We knew that the restriction was 2 minus x. X has to be less than 2 as well. Okay? What else is there? Was there anything else to do there? Okay, so now we just need to find stationary point. Let's go. Stationary point, how to find? V of x is currently equal to 4x cubed plus, what was it, plus or minus? Minus. Minus 8x squared plus 4x. Let's find the derivative. Yep. Oh, it can't be. Sorry. Because of that. Yeah. Because of the graph. Beforehand, I was just looking at the at this condition. But yes, you're right. From the graph, you can tell that it has to then be less than 1. Very good. All right. Find the derivative. What's the derivative? 4x cubed minus 8x squared plus 4x. Can I please have, let's go with Phoenix. Derivative 4x cubed minus 8x squared plus 4x. What does that give me? Beautiful. So this is my derivative. We're trying to find that stationary point, which is that turning point there. Stationary points occur when? When? When does it occur? When gradient 0, which is the derivative. So now derivative is v dash x. We need that to equal to 0. So let's solve for it. 0 is equal to 12x squared minus 16x plus 4. Factorize. All of this by hand. Obviously, if you did it on a CAS, it would be much quicker. Factorizing. I'm going to make it easier. Take out the 4 as a common factor. 3x squared minus 4x plus 1. That becomes 4, bracket, 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 bracket. Hopefully by this point we all can factorize 3x squared minus 4x plus 1. What does that give me? That's 1, 1, -3, -1. Yep, there we go. Solve for x. What does x equal to? What are my possible values for x? X is equal to? Good. 1/3 and 1. What does this mean? This means these are my possible stationary points. Now, if you look at the graph, it kind of makes sense as well. At x equals 1, yes, I had a turning point. We said it touches. So yes, that's true. Stationary point at 1. And the other one must be at 1/3. So here, I know this occurs when x equals 1/3. So that point up there, it's 1/3. But I haven't figured out what the volume is. Okay, because the question was asking, what is the maximum volume? Some students, after doing all this work, they're like, oh man, that was so hard, finally done. And they say 1/3. It's not 1/3. That's how much you're taking off from the square. So the volume, how do you work out the volume? What do you have to do now? How do you find the volume? So you want to find that. How do you find this? If you know x is 1/3, what do you do? You sub it back in. Now, when you sub it back in, just be careful which one you sub in. It's not the derivative. I see so many students do that in exams and SACs. Students have no idea what they're doing at this point, so they just sub it in wherever they see. Usually it's this one because it's the latest equation you got. So most students sub it back into the derivative, which doesn't make sense. That is to find the gradient. This is to find volume. So you sub it back here. Okay, so you sub back into v equals 4x cubed. So here we go. V is equal to 4 times 1/3 cubed minus 8 times 1/3 squared plus 4 times 1/3. Now that's a pain to do. I'm just going to quickly jump into the CAS and just type that in. Okay. Oh, this is my year 12. This is one of the year 12 equations. How cool is that? It's crazy, eh? All right, let's do new document. Actually, no, I'll do new problem. Calculator, let's define v of x is equal to 4 times x cubed minus 8 times x squared plus 4 times x. And we're finding v of 1/3. 16 on 27. So that means this is 16 on 27. There you go. So after doing all those calculations, the maximum volume that this can take must be 16 on 27 cubic meters. Okay, so write in your answer. Therefore, max volume is at 16 on 27 cubic meters. Okay, and obviously with this one, there is a bit of CAS work to do. Had we not done by hand, it would have been easier to do on a CAS. So you could have done all this on a CAS. So showing you when you get a problem where you don't get to use a CAS, that's the kind of steps you have to go through. And finally, find the values of x for which the volume is 0.5. That's pretty straightforward. CAS work, you're just saying when is the volume equal to 0.5? Solve for x. Okay, so it's really asking you to solve half is equal to 4x cubed minus 8x squared plus 4x. Find x. Do it on a CAS. So here we go. Solve for v of x equals 2.5, comma x. And these are my possible answers. Now just looking at the answers there, which one makes sense? Or which ones don't make sense? That's at least the first bit. -1. It's going to be negative, so cross that one off. You can't have half, but remember the restriction was between 0 and 1. So we're going to check, is this bigger than 1 or not? Okay, so here we go. It's bigger than 1, which was predictable because where's that 1.3 coming from? See, half is somewhere here. That's where half is. Well, actually, maybe that -1. Why is it? Oh, no, the -1 actually does fit. Do you know why? Because it's negative of this, but then it's positive of that. So 3 minus root 5 could still be a positive number, which makes sense. 0.19 is still positive. So this one is acceptable. This is acceptable. That's not acceptable. And how I knew was I looked at the graph and I realized if half is here, because 1's over there, if half is here, you got this point, you got that point, you got that point. This must have been half. And then that's 1 there. So this must be 1.3. That must be a positive number. So you got two numbers that you can see between these 2 points. So it says find values of x for which the volume is 0.5. Therefore, x is equal to 3 minus root 5 over, what is this, 4 and half. The other one you reject. It's the 3 plus root 5 on 4. Bigger than domain. So you take these two. All right. Now that was quite a bit of algebra, but what you can see is that ties everything we've been doing from the start of the year till now. That's why calculus is your bread and butter. It is literally 3/4 of your course next year. They can take any graph and do this. They can take a sine graph and do the same thing, and do log, exponential. In the exam that I just did before, that was a mix of log and exponentials in one. So you can see in this example, we did that kind of problem. Okay, so you can get equations that look like that. So that's one of the exams I was just doing. I'm going to do that with my year 12s. I'm going to show them how to go through this, but you can expect equations like these. It means you have to do the CAS, because doing this by hand, it's a pain in the butt. You're going to have to do all this by CAS. Okay, so you'll get problems where you have to get familiar with the steps, what you're doing, and then type it all in the CAS. Okay, so as you're doing this bit, practice with the CAS, but that's it for today's lesson. Today's lesson was telling you the difference between absolute max, absolute min. Absolute max is the largest Y value, min is the lowest Y value, and stationary points doesn't necessarily mean it is the maximum or minimum. It's just turning points. Okay? We'll stop the video there.